that they become more stable. Does anybody remember, we've talked about this, what makes an atom more stable? How is it going to become more stable? Peyton? It wants to achieve the octet rule, which means it wants to have 8 electrons in its outermost shell. Except for hydrogen's an exception. Let's look at hydrogen. So in hydrogen, how many valence electrons does hydrogen have? 1. Does it want 8? No, it does not. How many does hydrogen want to become stable? 2. Because if you look at the configuration for hydrogen, it's 1s1, but it wants to become like 1s2, which is helium. So hydrogen wants to be like helium. And so to do that, and hydrogen's a nonmetal. Hydrogen is not a metal, it's a nonmetal. So it's going to form a covalent bond with itself to become H2. This is the chemical formula for the stable form of hydrogen. Remember, the chemical formula tells you the number and type of atoms in a molecule. So now, this is the hydrogen molecule. A molecule is composed of covalent bonds. So anytime you hear reference to molecular compounds or molecules, they are being held together by covalent bonds. So these hydrogens by itself are just atoms. When it bonds with something else, it becomes a molecule. And to represent these shared electrons, we are going to replace the dots with a dash. And this is the structural formula. So the structural formula shows you the arrangement of atoms, not just the type of atoms and number of atoms, like the chemical formula. The structural formula shows how they're arranged. And when we get into learning about molecular geometry and the different shapes that the molecules take on, that's where structural formulas become more important. And we call this a Lewis structure, or a Lewis dot structure. And Lewis is the last name of the scientist who kind of came up with this method of representing covalent bonds. Not necessarily just covalent bonds, but when we did ionic compounds, we also did dot structures. So he came up with this system of representing the valence electrons and how atoms bond. And so we call this a single bond. I'm going to draw, let's see, I'm running out of space. This is a single bond. It's a single bond, meaning that a single pair of electrons is being shared. So you all know that 2 make up a pair. So 2 electrons here make up one pair of electrons that are being shared. And that is what we call a single bond. And this dash, the one dash, represents one pair of electrons being shared. And that's a single bond. Because tomorrow we'll learn about double and triple bonds. How many pairs of electrons do you think would be in a double bond? 2. How many in a triple bond? 3. 3 pairs. So that leads me next to talk about diatomic molecules. And I'm going to write the element symbols up here that form a name that I like to call Brinkelhoff. I think of it as, it sounds like a character in Harry Potter. Brinkelhoff. You'll need to remember that. These elements, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine, they will bond with themselves. They will bond with themselves to become more stable. They're much more stable when they become diatomic. What does the word di mean, di? Two. So two atoms bonded together. It's two of the same bonded together. So we just showed how hydrogen bonds with itself to become more stable, and it becomes H2. All of these other Brinkelhoff elements do the same thing. They form covalent bonds with another atom of itself to become diatomic. So whenever these exist alone, they always have the subscript of 2. There's always 2 of them bonded together because they are more stable in that form. And this is important when we start learning about chemical reactions and we start writing chemical equations and balancing equations. You have to remember that the Brinkelhoff elements, if they are by themselves, there's actually 2 of them bonded together, and they exist as diatomic molecules. Let's look at Cl. Let's do a dot diagram for Cl. How many valence electrons are in chlorine? 7. So they each want 1. Chlorine's a nonmetal. These are all nonmetals. So by sharing 1 with each other, now they have 8. So when I circle these 2 electrons, now both of these electrons belong to both of these elements. Think about like a Venn diagram. So whatever they have in common in the circle belongs to each. So now this chlorine has 8, 2, 4, 6, 8, and this one has 2, 4, 6, 8. And so we write the chemical formula as Cl2. The structural formula is just Cl-Cl. Alex.
In the Lewis structure formula, do we still put, like, if there is another, like, say, with, like, sodium chloride or whatever, if there's, like, a second molecule of one of those, do we still write the number, like, 2 or whatever, like we did with the other?
Are you talking about this?
Yeah.
Oh, in the chemical formula, the subscript? Well, that's what this subscript of 2 means. It means there's 2 chlorines. I'm not sure I quite understand what you're
Are
asking.
these only used for those? Are these structures only used for the diatomic molecules?
No, they're used for molecular compounds, which have covalent bonds. Nonmetals and nonmetals.
So if there was like a multiple, like, I don't even know if this is a pair, but like sulfur and chlorine, and like they needed different numbers and you needed to have more of one than the other, like, would you still have the subscripts in the structure?
Not necessarily. Molecular compounds do contain subscripts, and it tells you how many of each atom is in that. I think as we do more examples, it'll become a little more clear. Usually, what's going to be happening is you're going to given a formula like CH4, and you're going to have to show the Lewis structure for it. So you're told that it has 4 hydrogens. Whereas in ionic compounds, you're determining how many of each atom there are to get a net charge of 0. So this is really kind of totally different. So whatever you learned about ionic compounds, separate it from what we're doing here. The only thing that those are going to have in common is that when we write these dot structures for the elements, You still need to know the number of valence electrons. Other than that, the dot structures we did for ionics, just kind of put that aside. Don't forget it. Just put it aside for now. Okay, because this is totally different. We will not be representing transferring of electrons now. We're going to be using circles instead of arrows to share electrons. Okay, so there's our structural formula. So let's look at, let me go back to your book. Okay, we talked about single covalent bonds. Let's go over to page 227. We've talked about structural formulas. Okay, let's look at, we're going to talk about unshared pairs in a minute. Let's look at water. Let's do water. Something to say about this. This shows you the water molecule. There are different models that are used to show the arrangement of atoms in a molecule. This is called a space-filling model. And the larger red ball in the middle is your oxygen, and the little white spaces it represents your hydrogen. Yesterday, when we did our NOVA Elements app and you had to draw your molecular compounds, you were using the ball and stick model. You use little dashes, which are considered sticks, and that represents the bonds. And then you use the little balls that are different colors to represent the different atoms. So there's different models to show the arrangement of the electrons. Oh, yes. Do you have a note? Or she didn't give you a note, you just have to leave. Okay. All right. So let's look at water. All right, so H2O. So this tells us we have 2 hydrogens and 1 oxygen. Anything, when you start drawing these Lewis dot structures, when you're given a formula, anything that there's only one of is going to go in the middle. And then anything that we have multiples of will go around the one in the middle. So we're going to put hydrogens on the outside of the oxygen. So we need to start drawing our valence electrons. How many valence electrons are in oxygen? 6. How many in hydrogen? 1. Okay. Hydrogen, again, only needs 2 electrons to be stable. So it is going to share with oxygen to get its 2. So each of these hydrogens, by sharing 1 on each side of the oxygen, hydrogen's happy now. It's got its 2 electrons. That gives oxygen now 2, 4, 6, 8 electrons. So oxygen's happy. It's stable. So if we were to write the structural formula for this, we are going to replace these circle pairs, with dashes, and that is our water molecule. Now, that's not really how water is. That's not really how the geometrical arrangement of these atoms in water is. I'm sure you all have seen the arrangement for water in biology. Valerie? So we haven't talked about molecular geometry yet. But when we get to that, you'll learn why the arrangement is more like this and not linear like this. And it all has to do with these. These are called unshared pairs of electrons. That's one of your vocab words in this section. Unshared pairs of electrons. These are the pairs of electrons that are not involved in a bond. These are not involved in a bond. And so when I learned this in college, we called them lone pairs. Some books probably still do use the term lone pair because they're alone. So I may call these unshared pairs lone pairs.